Swayam Prabha. Digital India. Educated India.
In this lecture, let us continue our discussion on Wheatstone bridge circuits applied to force and moment measurements. In the previous lecture, we had introduced summing and differencing circuits. We are recalling the summing circuit here. In summing circuits, the resistances undergoing tension or compression are connected to opposite sides of the Wheatstone bridge in pairs. We recall that compression, compression, tension, tension on opposite sides. Once we apply the excitation voltage to the Wheatstone bridge, let us see what happens when the current flows through this path containing the resistances R1 and R3. So, let the current be I13. By Ohm's law, we get the current in terms of the applied voltage and the resistances which are in series. In a similar manner, you can calculate the current flowing through the other two resistors. So, the current comes up to this point and then goes along the route R4 R2, again converges at this point and continues. In that case, if the current is I42, then again applying Ohm's law, we get I42 equal to V by R4 plus R2, which are again in series. Once you calculate those currents, you can also calculate the voltages at 2 points. Let us locate these points. We will call this point as A and this point as B. We can calculate what VA and VB are based on the voltage drops once the current has moved through one of those resistances, either R1 or R4 respectively for VA and VB. What is the advantage of doing this? In that case, we should be able to get the output voltage, which is the potential difference between those 2 points. We keep the circuit diagram available with us here, and we continue to calculate the VAB, which is the difference between the potentials at VA at A and B respectively. So, if you do the mathematics here, you get this expression. Finally, on simplification, you get an expression like this, and finally, a ratio of delta V by V, that means the output voltage from the bridge by the excitation voltage, that would be given by this expression containing all the resistance values in the Wheatstone bridge. When the output voltage is 0, we say that the bridge is balanced. So, delta B has to be equal to 0 in such a case. When can that happen? Of course, when the numerator goes to 0. Again, that can happen if these two ratios are equal or all these resistance values are equal to each other. Let us say R. Now, if the load on the wind tunnel model changes, we have to remember that there is a wind tunnel model which is connected to a balance, and the strain gauges, which are basically the resistances that we are talking about, are bonded to this balance in some manner. So, when the flow moves past the model, it generates forces and moments, and that is transmitted to the balance. If you change the velocity of the flow or if you change the inclination of the body, then obviously the load on the wind tunnel model will change, and that would be transmitted to the balance. That is what we are talking about. the accompanying strain would influence the resistance of the strain gauges. So, because of the change in the loading, the strain on the resistances would also change, and therefore, their resistances, and consequently it will influence the delta V. That is basically the connection. If all the 4 resistances are changing or there is a provision for their changing, then we say it is a fully active Wheatstone bridge. If only 3 of them can change, then it is a 3/4 active bridge. If only 2 can change, it is half active bridge, and if only 1 resistance can change, it is called as a quarter active bridge. The most widely used one is the fully active bridge because of some accompanying advantages, which we will see later. Here is a diagram which actually is an example of a fully active Wheatstone bridge. That means, all 4 resistances can change, and it is found in the sting balance on which an aircraft model is mounted in the wind tunnel test section. We have a schematic sketch here which actually indicates that. We were talking about a sting balance. You can see the strain gauges indicated as 1, 2, 3, 4 on the upper and lower surfaces respectively of the sting balance, and when the force and moment system is acting on the body, which is in response to the flow that is moving past the body, you can expect that the upper ones will undergo compression and the lower ones will be undergoing tension. The resistances R1 and R2, they are being subjected to compression and they undergo a decrease in resistance. On the other hand, R3 and R4 will undergo an increase in resistance. Initially, if they start from here, then we have to account for the changes. The strains at locations 1 and 4 and 2 and 3 can be assumed to be nearly identical, and hence the corresponding resistance changes at those 2 locations are also identical. Let these resistance changes be delta R dash and delta R double dash respectively. So, the delta R dash corresponds to 1 and 4, delta R double dash corresponds to 2 and 3. So, let us try to write the change in resistances starting from the initial values, which were R, all of them were R, and now after the loading was done, let us say that they have different values and these are represented here. So, you can see that at locations 1 and 4, the change magnitude is given by delta R dash. In one case it is reduction, another increase, it is because of the compression and tension respectively. Similarly, at locations 2 and 3, the resistance change magnitudes are identical. Once you come back to that formula for delta V by V, you now have to substitute the altered resistances here for the respective terms here. So, once you do that and you do some simplifications by neglecting the higher order terms, you come to an expression like this. So, the delta V by V is nearly equal to this expression. Now, if these strain gauges are bonded very close to each other, that means 1 and 2 are close to each other, similarly 3 and 4 are close to each other, which means they are very compactly bonded on the strain gauge, then what will happen is that delta R dash and delta R double dash will be nearly equal to each other, and let us say we call it delta R. In that case, delta V by V will become delta R by R, which means there is a linear relation between delta V and delta R. This happens for an active bridge. It is not going to happen if you operate at 3/4, half or quarter active bridges. Thus, fully active bridge configuration is the preferred one for measurement purposes. Additionally, we find that there is temperature dependence of resistance. Now, if all of them are active, even temperature compensation is easier to do in such a bridge. So, we discussed about the summing circuit, let us discuss about the differencing circuit now. We recall this figure which we did in the previous lecture. So, what is the difference here? In differencing circuits, a pair of resistances undergoing tension and compression respectively are connected to opposite sides of the Wheatstone bridge. So, you have a compression here with a tension here. Again a compression here with a tension here. So, that is how you distinguish or identify a differencing circuit. And again let us say the unstressed strain gauge resistances are R1, R2, R3, R4 respectively, and we follow the same procedure essentially as we did for the summing circuit. We calculate the current through the sequential resistances, and then we find out the voltages at the points A and B, then find out the delta V across those 2 points and come to this. You should be able to work out this relation for yourselves at home. And then comes the point where we talk about the change in resistance because of the applied loading, and therefore, the delta R and delta R dash and delta R double dash getting into the calculations, dropping out higher order terms etc., you can come to a point like this. So, what we understand from this relation is that if the strain gauges are pasted very close to each other, which means that delta V will be nearly equal to 0, because if you bring them close, again additionally delta R dash will limit towards delta R double dash. That means, delta V will tend to 0 as you bring the resistances close to each other. And of course, if you keep them far apart, you are going to get larger delta V for the same excitation voltage. Let us discuss about more specifically about internal sting balance, which we had already indicated through this figure. So, a balance which is inside the test section of the wind tunnel would be called as an internal balance, and when it has a sting kind of a nature where it holds the model from its base or from the rear portion, we know that it is called as a sting balance. So, we have drawn the schematic diagram where the internal sting balance connected to the model is demonstrated schematically. The strain gauges are bonded on the sting and connected in a Wheatstone bridge arrangement. So, before you bond it on the sting, you have to prepare the sting surfaces very carefully by machining them to appropriate surface finish, keeping the surface very clean before you bond the sting bond the gauges to the sting surface. When the wind tunnel is started, the forces acting on the model change the resistance of the strain gauges, and for each component of force and moment that has to be measured, a separate Wheatstone bridge has to be formed. This is a very important point. So, depending on how many components of forces and moments you are trying to measure using the balance, you should have an equal number of Wheatstone bridges configured using your sting balance. So, for example, if you are talking about a 6 component sting balance, it would require 6 Wheatstone bridge circuits consisting of 6 into 4, which is 24 strain gauges, because each one of them consume 4 gauges. You would need a 6 channel signal conditioner, 1 channel dedicated to each bridge, a separate power supply for each channel, and an appropriate data acquisition system which can handle the 6 channels simultaneously. So, this would broadly be the total setup for acquiring the load data. The sting is attached to the model and it moves or reorients with the model. So, the movement of the sting is coordinated with the movement of the body. Hence, the forces and moments are easier to measure about the body axis, because the sting and body axis are identical and the forces are being measured in that axis system, not the direction along which the wind blows, which is basically referred to as the wind axis. However, you may need to do some transformation in order to convert forces which are measured in the body axis system to forces which are easier to refer in the wind axis system. For example, you measure normal and axial forces in the body axis system and get them converted to lift and drag using the angle of attack of the body in the wind axis system. So, what we are basically trying to say is that this orientation is not going to remain fixed. If this is a certain angle of attack, you are going to change it you are going to do the experiments over a range of angles of attack, and that is perfectly fine. A little more detailing of how we measured lift and which kind of circuit should we be using for that. Let us consider that the air flows past a symmetrically placed aircraft model. To keep things simple, we are doing that, and that basically means that we are keeping a 0 angle of attack. In that situation, though we are going to actually measure normal force and axial force, they would basically mean lift and drag forces, because your angle of attack is 0. So, if you are measuring say 3 components, lift, drag and pitching moment, then you would need a 3 component balance, and when angle of attack is 0, then the normal force that you measure using that balance will be the same as the lift force, the axial force that you measure will be the same as the drag force. So, we are purposely discussing about such a situation, because the angle of attack does not explicitly enter the calculations in such a situation. The sting is basically like a cantilever beam element. The lift force and pitching moment produce bending stress, and the drag force creates axial stress, basically compressive stress. So, we have to keep in mind that pitching moment as well as lift force are responsible for bending stress, and therefore, both their effects have to be accounted. When a differencing circuit is used, the output voltage is proportional to lift force only. This is something that we will demonstrate soon. Here we are stating it. Now, we already found out that for the differencing circuit, delta V by V is given by this expression, and now we are saying that whether it is delta R dash or delta R double dash, we have to account for the change in resistance due to the bending effect, the bending stress effect. Here we are considering that as a positive quantity, while the axial stress will always be of the compressive kind, and therefore, would reduce the length of the resistance, and therefore, it is a negative sign all the time. We do that for both the dash as well as the double dash quantities. So, delta R dash comprises of elongation effect due to bending produced by lift force, and hence positive change in resistance, and contraction effect due to drag force, hence negative change in resistance. The subscript B stands for bending and subscript A stands for axial force, which is imperative. The bending creates different values of strain along the length of the sting, and hence is a function of position. So, whether it is a dash or a double dash location, the change in resistance will be different at these 2 locations. However, the axial force creates the same value of strain irrespective of location, and therefore, this is not accompanied with a dash or a double dash. Remember that when it is applied to an element which is under tension, then this bending part leads to increase in resistance, while if it is a compressive element, then the same term will actually be accounted as a negative term, because the resistance decreases under compression. We do the calculations here, and we find out that the delta R A cancels out. So, the output voltage is independent of axial stress. Now, we invoke the gauge factor, which we had studied earlier, and we find that the gauge factor can be represented as delta R by R, the whole divided by epsilon, which is the strain produced in the resistance due to the applied loading. Therefore, a change in resistance can now be expressed in terms of the resistance value itself, the gauge factor and the strain. Now, let us recall about normal stress and normal strain at a section of a cantilever beam. So, this you must have studied earlier in your strength of materials courses. Normal stress at a section of the beam sigma x would be given by my by I, which is the bending or flexural stress formula. Now, m is the bending moment, y is the distance from the neutral axis which passes through the centroid of the cross section of the beam to the fiber on which stress acts. So, either it is the upper surface or it is the lower surface that we are interested in as far as that y distance is concerned. So, if you consider its thickness to be 2h, the y will essentially be considered as h, which is basically the distance that we are talking about. I is the moment of inertia of the cross sectional area about an axis which passes through the centroid of the area. So, these are standard nomenclatures or implications, but we are just trying to revise that idea. And a very important idea is that normal stresses from axial and bending loads, they will be added together. Consequently, the axial or normal strain at that section epsilon, which we already talked about over here, will be represented as sigma x by E, E being the Young's modulus, and therefore, the epsilon expression comes out to be my by EI, which we need to remember. In these expressions, you see the application of that formula that we just looked at, my by EI. So, what are we talking about? We are talking about the situation being represented like this as a cantilever beam on which 4 resistances in the form of strain gauges have been attached at locations 1, 2, 3, 4 respectively. It is supported here at the end. The locations of those resistances are provided here from the end. There is a tip loading, and this is the thickness of the cantilever beam. Now, in this diagram, the force acts at the tip of the cantilever. That is an ideal situation, but in a sting balance, the lift force does not act at the tip of the sting, but further away from the tip. You can figure out here in this diagram partly that the lift force may be acting at a distance here, and that is not exactly the tip of this sting balance, because this is the extent of the sting balance, and certainly the applied force does not act here. So, we will consider that that distance is z from the support. So, let us say if this is the location at which the force is acting, then this is the z distance that we are talking about. So, if you consider that, then at location 1, the strain that we will have is epsilon 1 with a negative sign because it is compressive, and then L times z minus z 1 is basically the moment. So, z minus z 1 being this distance is basically the moment arm that load gets to act on that point 1, and then the rest is here, h is the y distance and E I at the bottom. So, in a similar manner, if you look at epsilon 2, that again due to compression has a negative sign here, the accompanying distance z minus z 2, and then the corresponding strains at points 3 and 4 can be very easily obtained if you equate them with the negative values of epsilon 2 and epsilon 1 respectively. Remember that these are positive strains. Now, based on this relation that we learnt a few minutes back, that delta R is equal to R G epsilon, we can now find out what is the changed value of the resistance based on the strain that is exercised at that location. So, likewise R 1, R 2, R 3, R 4 are worked out here. Now, a little bit of substitution. The output voltage of the bridge, the standard formula is known to us. We now have to substitute each one of those resistances in terms of the strain effect, and then do some simplifications based on neglecting higher order terms etcetera, which we already talked about, and this is the approximate expression at the end that we get. So, the output voltage is linearly proportional to the lift force, because the epsilon to epsilon expressions now come into the picture, which we have shown in the previous slide, and the final expression boils down to this. All right. and therefore, you can figure out that it is linearly proportional to the lift force. The K1 is basically a constant comprising of gauge factor, the distance between the locations 1 and 2, h by EI. Obviously, the circuit can be made more sensitive by increasing the distance between the two sets of strain gauges. So, for the same excitation voltage, if you want to increase the delta V, this is a very convenient way of doing it. Based on the length of the strain gauge, you try to maximize Z2 minus Z1. Automatically, the sensitivity of the sting balance will increase. Again, linear relationship that exists here is because you are using a fully active Wheatstone bridge. Now, let us discuss about measurement of pitching moment. We discussed about the differencing circuit coming to use for measurement of lift. Now, it is anticipated that the summing circuit will be getting us the pitching moment, but how? Let us try to figure out that. We recall this formula that we already talked about for the summing circuit, and now after substitution of the expressions for each resistance in terms of bending and axial strain related resistance changes in the above equation and neglecting higher order terms, this is the first step which will bring us to expressing delta V by V in terms of the change in the resistances due to the bending effect at the two locations which correspond to the dash and the double dash locations. The above expression is independent of the axial stress due to the drag force, it is imperative, because the delta R A does not figure in this equation. It only contains the bending stress effect. Expressing the above equation in terms of epsilon, which we just discussed in the previous two slides, we can now convert that expression in terms of the epsilons. So, this is the expression you will get as a consequence. Let us try to rewrite it like this. We break it into two terms, and then we can write the first term as minus K1L, the second term as this, which is nothing but another constant into the pitching moment. So, what have we come up with? We have come up with an expression where the output voltage from the Wheatstone bridge is going to be connected with both the lift and the moment. However, we want it to be effective for pitching moment measurement, not a combination of lift and moment. So, how do we do that? Let us try to see. Moment, of course, over here is this, K2 is this constant, and let us see how much this first term will actually influence the result. The output voltage, as we can see, is dependent on both lift and pitching moment. However, it is to be noted that K1 for the summing circuit is made very small and therefore is negligible, because K1 depends on Z2 minus Z1, and if we are bringing the strain gauges extremely close to each other, then this becomes a very small value, nearly equal to 0, and therefore, essentially this term will go away from your expression. So, this becomes small and the summing circuit therefore becomes effective in calculation of the pitching moment. And in differencing circuit, you remember, we took a completely different stance, we kept them far apart so that we could increase its sensitivity. So, the strategies that we are using are diametrically opposite. So, in this lecture, we discussed about Wheatstone bridge circuits for force and moment measurement. The summing and differencing circuits were discussed in detail to bring out their suitability for measurement of moment and force components respectively. In the process, you also got to learn how you need to locate the strain gauges on your balance, so that you make it either effective for force measurement or moment measurement. Thank you.